These are the notes for LT3 in the sound and wave unit. Target says, I can apply sound reflection and refraction to real-life situations. Reflection and refraction. Most of what we focus on will be sound waves, but we will talk a little bit of light as well here. So, two very different concepts. Okay, reflection and refraction. Don't let those R's get in your head. They're two different things. When you think about a reflection, think about a basketball rebound. All right, you get a bounce. Right, things bounce if it's a reflection. So the waves bounce off objects. If you're in class, you know we do a activity with a protractor where we know that the angle a wave hits, it will bounce off at a corresponding angle. Okay, if you throw a ball against the wall, depending on the angle at which the ball hits the wall, that's going to determine the angle that the ball reflects or rebounds, so it reflects off the wall. What's really important to know with sound reflection is there is no change in frequency or wave speed. Okay? So the pitch of the sound wave would not change, the speed of the sound wave would not change. Right? Just so we can kind of talk some commonalities here, the speed of sound in air is right around 340 meters per second. If it's the activity we do with the protractor, we call it 343. It's right around 760 miles an hour. So it's pretty fast, not nearly the speed of light, but pretty darn fast. Let's apply this, because who cares? Waves bounce lengths, what does it matter? All right, that's an echo. So speaking of echolocation. When we think echolocation, a lot of people think dolphins. That's absolutely 100% accurate. We call it sonar if it's underwater. Think military submarines, that would be sonar. If you're in class or if you click onto Moodle, there is an excellent link that will take you to a YouTube video dealing with dolphins. All right, so I'm sorry, not dolphins, bats. So we're going to list them first. Bats, dolphins, subs, not a subway here, but actually submarines under the water. Ocean miners use these sound waves to map the ocean floor or to look for potential places where there's oil. So regardless of what your viewpoints are on mining within the ocean, that is one of the uses of echolocation. But I urge you to click onto Moodle, watch that YouTube article about the bats because it's pretty cool. But I'm going to attempt to just draw the idea. You guys know how well this is not going to go. So here is the bat. Here, it's got little bat ears. There we go. Looks like horns, but it's not devil bat. And here's my bat wings. So this is something straight out of Count Dracula. Oh boy. Oh man. Those are not so good. Not horrible, but not good. So we've got a bat. In the video, it's going after a moth. So down here, I'm going to draw its parent. Looks like a unicorn for Pete's sake, but there's not a butterfly, it's definitely a moth. And what happens, if you've ever listened to a bat, you can hear some of the squeaking. Alright, so some of the squeaking, the chirping the bat makes is within our range of hearing. Remember, we hear anywhere from 20 hertz to 20,000 hertz. We still say, though, that they use ultrasonic waves because some of their squeaks will be at 20,000 hertz and above. All right, so some, if we can hear them, we know they're not here because we can't hear that frequency. But some of them will be in there. And so what these bats do is they're going to emit these sound waves at a very specific frequency, and they are looking for them to hit an object. Okay, when they hit this object, some waves will bend around it, but a lot of them will bounce back. And when they bounce back, they're going to lose some energy. They won't come back as loud as they were sent out, but their frequency will be exactly the same. Okay, there's nothing that is going to change the frequency of these waves as they come back. So we have an outgoing wave I have in black here, and then an incoming wave back to the bat is in green. Okay, so even though there's no change in frequency or wave speed, you will see a loss of energy. Remember, a loss of energy would mean a loss of amplitude because some of that is going to get absorbed within the medium. Think about the dominoes. Some of the energy is put into knocking the dominoes over. Same thing, some of the energy is being put into vibrating those gas-air molecules to move the waves back and forth. All right, so loss of energy, but frequency wavelength stays the same. They can hone in. If you're in class, we also watched the video link of how visually impaired folks are learning to use the same process. So I urge you, now I'm second guessing myself. I feel like the link is on Moodle, but if it is not, type into YouTube echolocation visually impaired, and you will find videos that show how people who have trouble with their vision are learning to use this very same process to navigate. So instead of using the stereotypical leader dog, cane, that sort of thing, they're able actually to make sounds. Okay, that's reflection. Okay, bouncing the waves off, nothing changes except amplitude. The fancier one today is refraction. Okay, refraction. Refraction, straight up definition first. This is a change in wave speed. So a change in wave speed which causes waves to bend. Okay, so you got to think about what could possibly change the speed of a wave. Once the sound wave is out of your mouth, what in the heck is going to speed it up or slow it down? It's gone. The only thing that can change the speed of the wave, no exceptions here, is it changes speed when entering new mediums. So when. So sound, we know, hopefully, travels the fastest the more dense the medium is. Okay, so if we have medium in this column and the speed of sound in this column, let's say that the medium is air. We said that the sound travels about 343 meters per second in air, varies a little bit based on air temperature. Water, sound travels 1,500 meters per second. A liquid is more dense than a gas, so it makes sense. The molecules are closer together. Again, think domino lab. So therefore, the sound wave is going to propagate, move faster within water. Steel, more dense yet. Sound travels 5,000 meters per second in steel. Okay, so what would happen is if a sound wave is cruising through the air and then it hits a window, it's going to bend when it hits the window. Okay, it would cause a bending of the wave. And then it would cruise through the glass. And then when it enters out the other side, let's say that you're yelling through a window at somebody, when that sound wave finally makes it through that window, it's going to change speeds again because it's going back into a gas, and it would bend again. All right, so I know that maybe you need to pause me to wrap your head around that. But we know that it's going to be the fastest here and the more dense. Okay, I think more dense here. And then less dense, it's going to be slower. We know in the vacuum of space where there is no medium, to keep this as simple as possible, there's no dominoes to move the wave. There's no medium, there is no sound wave. So we don't even need to put that on here. All right. Now, this is really easy to see with light. Most people have seen, like, you fill a beaker with water, stick a pencil in it, and it looks like the pencil is broken. You dangle your legs over the edge of the pool, and you look like your legs aren't even connected to your body. All right, it's that weird illusion look because of the fact that waves change speed, they refract in different mediums. Sound is tougher to do with this. It's tougher to kind of think of an example. So I'm going to squeeze this in here I think I can get it right here. We're going to have two versions of this. And we'll do it like this. I'm going to just get this out of there so we can see the difference. Let's have daytime. So we'll put the sun out here. All right, here we are in the daytime. Sound does not carry as well, which means it does not travel as well during the day as it does at night. So if you are here and you say something during the day, all right, if you say hi during the day, your sound waves, as soon as they leave your mouth, if you're talking in a classroom, as soon as the sound leaves your mouth, it spreads out equally in all directions. Unless you've got your hand over your mouth because you're whispering deep, dark secrets to your table partner, those sound waves go in all directions, because for the most part the air is uniform in temperature. I understand lens heat rises, so that, yes, it is a little bit warmer towards the ceiling, let's say, than it is towards the ground. But for the most part, if it's middle of the day, as soon as you say something, your sound waves travel out equally. Now at nighttime, it's a different story. If you've ever been camping or been on a lake at night or been outside when it's nighttime, you can hear everything. And part of it is, yes, there's less commotion about, but there's also some science to this. So if it's night, here, let me try to draw a moon. There we go. So there's our little half moon out, and you're out here at night. We haven't talked about heat capacity yet, but for right now, you'll just have to trust me that I'm going to make sure I don't have this mislabeled, that at nighttime, the ground cools faster than the air. All right, we haven't talked about why yet, so for right now, just realize that it will be cooler towards the ground. And cool air does not allow the sound to move through it as quickly as warm air. And it's almost like the sound waves get bogged down. So when you start to talk at night, they're like, whoa, it's warm up there. They will bend towards the slower medium. Okay? So that's important to know. Sound waves bend towards the slower medium. So you'll be talking here without a mouth. I don't know how you did that. There we go. And as you start to talk, you'll see these waves shift towards the ground. Now, realize most people are on the ground, so therefore, if you've got a friend way over here, they will hear you way better than that friend if they were over here during the day, because the sound waves will bend towards the slower medium. Because most of you know I'm a camping addict. I spend more nights in my camper than I do at the house in the summer. You're out sitting around the fire at 10 o'clock, you can hear stuff 3-4 sites away. All right, you can hear everything because those sound waves that you're generating stay towards the ground, and that's where we are at. So daytime, they spread out evenly, and you're just going to lose energy. It's not going to carry as well. But at nighttime, they bend towards the slower medium, which is the cooler air. It doesn't allow it to move as easily. And so it refracts, it bends, and sound carries better. This tends to be a tough target in terms of scores. All right, so really spend some time, see if you could explain what's happening there without looking here, that sort of thing. Alrighty, that's LT3. Good luck.